this video, we're going to talk about the three fundamental concepts of position, velocity, and acceleration. We're going to talk about just defining the terms, but then also how they relate to each other in terms of calculus concepts which underlie physics. Okay, let's start with defining things. Position. Position will always be represented by the letter x in any equation that involves position. Delta x, or change in x, is defined as displacement. So when we talk about displacement, what we mean is change in x, or the difference between the final position and the initial position. All right, velocity is the rate of change in position. The units for velocity are always meters per second because a velocity is telling you how quickly your position changes with respect to time. In calculus terminology, that's represented like this. V, it says, equals dx dt. What does that mean? Well, okay. X would be position. When you see this, it means the derivative of position with respect to time. You should remember from previous material that a derivative is a slope. This statement here means that if you have a graph of position versus time, the slope of that graph, the derivative of that graph, is velocity. So that's what this is indicating. All right, let's show what that means graphically. I have here a graph. It is let's make it like this, a position versus time graph. Oh, look at that thing. Okay, if velocity is the derivative of a position versus time graph, then if I have a graph that looks like, say, this, or maybe this, the slope of each of these sections tells me the velocity of the object, whatever it may happen to be. So this slope is the velocity of the object over this time interval. If I were looking at this time interval here, then of course that would be a different slope, and therefore whatever the velocity is of the object over that time interval. Either way, if it's a position graph, position versus time, the velocity is the slope of that graph. All right, this statement is telling me something else. If I have this is the sign for an integral. So what this is saying is displacement, as we defined it over here, is the integral of velocity with respect to time. Meaning if I have a graph of, let's say, velocity versus time, and it looks something like, I don't know, this. If I want to know how far has the object moved between this moment and this moment, the integral of this graph is going to be the displacement. Okay, again, back up to previous material, what was an integral? Geometrically speaking, an integral is an area. So if an integral is an area, and I say, how far has the object moved over some time interval, you would figure that out from this statement by finding the area of this triangle. That's it. That's all you'd actually have to do. The area here would be the displacement because this is a velocity versus time graph, and the integral of velocity with respect to time is displacement. Okay. We move over here to this final column, acceleration. Acceleration is always represented by the letter A. It's the rate of change in velocity. So it says how quickly your velocity changes. And then in calculus terms, acceleration is the derivative of velocity with respect to time. Again, a derivative is a slope. So if you are looking at a velocity versus time graph, such as this one here, the slope of this line is the acceleration. Okay, so that's the basic connections between those concepts and the kind of information that you can get out of the graphs, right? If it's a position versus time graph, the slope can tell you the velocity. If it's a velocity versus time graph, this is kind of the one you get the most out of. The area can tell you the displacement, and the slope of it can tell you the acceleration. Now, you might be looking at these graphs and wondering, like, why the relationships are what they are. Well, how do I know that the slope of this graph is a velocity or whatever, and those kinds of things. So I want to make a connection here based on the units for the axes of these graphs, so you understand, graphically speaking, like why is the slope of this a velocity? Or why is the area under this curve going to be a displacement? All right, so let's come over here to this one. Let me add some numbers to it so that we can say, like, just for the sake of argument, right, why would the slope mean what I'm saying it means? Suppose that after, I don't know, 4 seconds, the object here has traveled 20 meters. How about that, right? Well, how would you calculate the slope? Well, okay, the slope would be the rise over the run. And unlike a lot of problems that you've done previously in math class, where it's just like find the slope of the line, this slope has units. Slope being rise over run, I would say the rise is 20 meters. Not just 20, but 20 meters. And the run is 4 seconds over this interval. Divide that out, that would be 5, but not just 5, it would be 5 meters per second, which you should recall are the units of velocity. Velocity is always going to be measured in meters per second in physics. So therefore, the slope of a position versus time graph has units of meters per second, confirming what we just said here, right? That the velocity is the derivative or slope of a position versus time graph. All right, if I have a velocity versus time graph, such as this one right here, let me erase that little bit down there. We'll get back to that later. Suppose that, I don't know, the initial velocity of this object at this moment is, how about 4? 4 what? Oh, 4 meters per second, because that's the unit for velocity. And this is happening, right? It crosses the axis at, let's say, I don't know, how about 2 seconds? Okay, I said the area of this is displacement. Well, how do I find the area of something like that? Well, the area would be, well, let's see, it's a triangle, so 1/2 base times height. Let's see, the base is 2 seconds. 2 seconds. The height is 4 meters per second. When you multiply this all out, what it's going to tell you is that the area is, again, not just a number, it's 4, okay, but it's 4 seconds cancels, so 4 meters. The area here is 4 meters, and that means that the object has traveled 4 meters in this 2-second interval. All right, if we have the slope of this instead of the area, we can apply the same concept that we did over here, slope being rise over run. The rise in this case would be, well, let's see, -4 meters per second. And the run is 2 seconds. So therefore, the slope of this segment here is going to be -2 meters per second, or if you prefer a more compact terminology, -2 meters per second squared, and those were the units that we said we always use for acceleration, because it tells you meters per second, the rate of change in the velocity of the object. Okay, so in this way, you should be able then to see that the units of the slope of this graph are acceleration, and therefore, what I said, right, the slope of a velocity versus time graph is the acceleration, because acceleration is the derivative of velocity. This portion of the video is going to be devoted to a calculation-based question on graphs and the kinds of things that they might ask you about. So in this particular prompt, you are given a graph of, it says velocity versus time. You can see there's some numerical values on here. So from this information, we're supposed to, part A, find the acceleration. Well, let's see, what is acceleration? How does it relate to a velocity versus time graph? Is it the integral or the derivative? Oh, it's the derivative. There we go. Now we've got it. Okay, what's a derivative? Oh, a derivative is a slope. So basically, all part A is asking you to do is find the slope with a line. That's it. So you can use whatever section you want. It's a straight line. We can figure out that the slope is negative 16 over 20. Okay, and if we simplify that fraction, that's negative 4/5 or negative 0.8, whichever one you prefer. And the units for that would be meters per second squared. Perfect. All right, part B asks you to find the displacement from the origin at, all right, and then it specifies a bunch of different times. Whenever you're asked to find the displacement from the origin, it means from the initial moment, right? From the initial position where it begins, right? Assuming that it starts at the origin, which usually for these kinds of questions it will. So if we want to find the displacement at the 10-second mark, that means that we are finding that area right there of that trapezoid, as it turns out. The area of this trapezoid happens to be 120 meters because it's a displacement. Displacement is the integral of velocity, meaning it's the area under a velocity versus time graph. Okay, so that means that the area is 120 meters, and therefore at 10 seconds, the object has, or after 10 seconds, the object has traveled 120 meters. All right, now we can put that into some kind of a table. I guess I'll do that here. Okay, if you churn through the rest of the calculations, you'll discover that at 20 seconds, this area here is 160 meters. Oh, great, okay. All right, if you go on to 30 seconds, though, there's something maybe kind of weird that happens here. It turns out in calculus, there's such a thing as a negative area. Whenever you're trying to calculate the area under a graph, it's always relative to the x-axis. So sometimes when people are given this question for the first time, they'll like freak out and draw a new line here and like find the area of this triangle. No, that is not correct. You're not finding the area of this triangle. Rather, what you're doing is you're finding the total area from this triangle and this triangle. But when I say total, it's not what you think. Area above the x-axis is positive, whereas area below the x-axis is negative. So this area right here, if you work it out, is negative 40. So that means that after 20 seconds, the object has traveled 160 meters, but after 30 seconds, it's traveled, well, the total of 160 and negative 40 is 120. So in other words, after 30 seconds, its position is now only 120 meters from the origin. If you think about what that must mean, it means that starting at this moment, it's now going backwards. At t equals 40, this negative area is now negative 160, which means that at 40 seconds, it has returned to its starting position. So the total displacement over this 40-second time interval is in fact 0. Okay, so again, remember, area above the x-axis is positive area. Area below the x-axis is negative area. And in the case of like a velocity versus time graph, what that would indicate is forward motion and then reverse motion, right? And therefore, based on these two areas, this object is ending exactly where it began. All right, so let's see. Let's do the other things. It says draw a graph, meaning draw a graph of displacement versus time. Always for these graphs, unless I very explicitly say otherwise, start at the origin. That's where it starts, okay? At 10 seconds, it's at x equals 120. So 120 would be like maybe here. At 20 seconds, it's at 160 meters. So that would be like here. At 30 seconds, we said it's back to 120. And then at 40 seconds, it's back to the origin. All right, let's connect the dots in as smooth a manner as possible. But just at a glance, you should be able to see, oh, hey, this is going to be some kind of a parabola. Okay, describing this object's motion, signs indicate direction. Okay, let's review a little bit. When we say that something has a positive velocity, which it has over this time interval, positive velocity means moving in the positive direction. Negative velocity means moving in the negative direction. And of course, zero velocity means that something is stationary for an instant. So if we were to describe the motion of the object, we would say that over the first 20 seconds, it's moving in the positive direction, but more and more slowly, right? So it's doing like this. At 20 seconds exactly, it stops for an instant. And then after that moment, begins to accelerate faster and faster in the negative direction. Although actually, if we're careful in our thinking, we would say the whole time the acceleration is in the negative direction. It has a negative acceleration for the entire time that it's in motion. Okay, so initially what that means is it's moving in the positive direction with a negative acceleration, therefore more and more slowly, stops at 20 seconds, and then begins to accelerate in the negative begins to move in the negative direction faster and faster, right? Okay, so I guess I did my fingers wrong, right? Velocity, acceleration, stops, whoa.
Velocity, acceleration, stops, whoa.
I like how that looked on the screen.